We are continuing our factoring lessons, and we are going to focus on special products today, which we can use all the methods we've done with factoring, GCF, trial and error. If you really wanted to, you could factor by grouping, but if you can pick out these characteristics, you can factor it a little bit quicker. So we're going to go ahead and start with perfect squares, and we've all seen these before, and we foiled them, but now we're going to reverse it and factor them. So this is what a perfect square will look like. It will start with a perfect square, it will end with a perfect square, but the only way that it factors as a perfect square is if it's twice the product of these roots. So it will look like this, a plus b quantity squared. So I just want to go off to the side here and do a little bit of work on that. If I have a plus b quantity squared, the first thing I need to remind you is that you can't distribute a power over addition and subtraction. You would actually write it out as a plus b times itself. Those power properties are only for multiplication division. So no distributing a power, you write it out times itself. And when you have a binomial times a binomial, we FOIL it. So first would be a squared. The outside would be a positive ab. The inside would be a positive ba or ab. And last would be a positive b squared. And then you can see we have these like terms. So we have a squared plus 2 of these ab's plus b squared. And so we are going to have our multiplied out perfect square, and we're going to get back to factoring it. And anytime you have something times itself, you want to write it as a quantity squared. So the shortcut to foiling this is you square the first term, you square the second term, and you take twice the product of the roots, and there's your 2ab. All right, now, if the middle term is negative, that is not a big change. If the middle term is negative, you would come in and you would have your a minus b quantity squared, which is a minus b times a minus b. So we still get that positive a squared, but this time we get a negative ab for the outside, a negative ab for the inside, and a negative times a negative gives us back that positive b squared. And you can see that that transforms with our like term to negative 2ab plus b squared. So again, when you have a positive c, that means you must have a plus plus or a minus minus to get here. And so that would bring us to the minus minus. Now, just because it looks like a perfect square doesn't mean that it always is. We're just going to try that first. So, first rule of factoring, don't forget your GCF. That's our first rule, and then we're going to look for the pattern. So a perfect square is always going to be a trinomial where the first and last term are squared. So that is x times x, and this could be 3 times 3. Now, this truly is that easier factoring where a is 1, and the factors in 9 will add up to 6, 3 and 3. So if I drop this down, I always suggest you try this, you don't just jump to the answer so you can test it. It'd be x times x to get my x squared. And my last, I'm going to do a plus 3 and a plus 3 because there's 3x and 3x to get 6x. Now, to get full credit, when you have something times its exact self, it's written as x plus 3 quantity squared. And that shows that you have found a perfect square. All right, now, typically we wait to this, oh, that's harder factoring because a is not 1. But take a minute and look. 4 is a perfect square, and so is 25. So it might be worth your time to get a list of perfect squares on a note card. And so I will show you what I have here real quick. I forgot to show this earlier. I have the steps for busting B or factoring by grouping. But over here I have the list of perfect squares. 1 squared, 2 squared, 3 squared, 10 squared is 100, 11 squared, 12 squared, up to 15 squared. These are pretty quick to remember. 13 squared is 169, 14 squared is 196, 15 squared. So we're all familiar with up to 144 because of our multiplication table. These numbers are on the diagonal. If you want to see if something's a perfect square, you know, I have a number 196 and I just want to test it, just go into your calculator and take the square root. If you get a whole number, it's a perfect square. If I was trying to take the square root of, you know, 200, I would get that irrational number. Okay, so that's how I can test if it's a perfect square. So here are my square numbers, so you have them, and here are my cubic numbers that we're going to use in another chapter when we do difference in sum of cubes. So you might want to pause this and jot these down, but it's always good to have a reference as you're working and get more and more familiar with these numbers. It's going to make your math a little bit quicker. All right, so back to here. These were on my list of perfect squares. So rather than just trying any numbers, remember 4 could be 2 and 2 or 4 and 1, and 25 could be 5 and 5 or 25 and 1. So I could be using my trial and error, but the factors of 25 will not add up to 20 because this is going to change it. So I'm going to try the 2p, and I'm going to try it with a positive 5 and another positive 5. Now double check. Again, we know the first works, we know the last work, but you need to check that outer and inner. Okay, so you're always wanting to double check. So 10p and 10p, there's your 20p. To get full credit, 2p plus 5, quantity squared. Okay, so then we're having this pattern, and I jump to here, and 50 is not a perfect square, and 8 is not. Please don't make this harder than it is. GCF is 2. Take that out, you're left with a 25k squared plus 20k plus 4. All right, now if you look, you can see that we have the flip-flop of these. So probably not our best second example or third example, but it will do. And so we're going to do trial and error, but we're focusing on the perfect squares that we have. So if we see that, that makes our trial and error a little bit easier. 5k, 5k, and again we want all positives. And so if I double check it, the first and last work, outside's 10k and 10k, there's 20k. So keep that 2, and then what we have is 5k plus 2 quantity squared. Final answer. But it's very important to get there and check. All right. Now we're going to flip-flop, and we're going to do something that looks really different. This has come up in this has come up in a couple worksheets. See how I have only 2 terms? Look, p squared minus 81, 25 minus x squared. We only have 2 terms in all of these. So that should tip off. If it's a difference of 2 squares, I only have 2 terms. So always GCF. If there's 4 terms, I'm going to factor by grouping. If there's 3 terms as a trinomial, I'm going to try reverse FOIL with trial and error or grouping or something like that. So as I was saying, because I got stopped here, if we have 3 terms, factoring by trial and error, grouping, it's going to look like that reverse FOIL. But now we know we can maybe pick out perfect squares, and if there's 2 terms for now, we're looking at a difference of 2 squares. It literally is exactly what it says. It has to be a subtraction sign or it won't work. So difference, p squared, p times p, 9 times 9. Okay, it has to be a difference of squares. Eventually we're going to talk about a difference in sum of cubes, so we would have powers of 3 and numbers that have a power or a power of 3. So how does this work? Well, if you really take a minute and look at it, it's a squared plus 0ab, oops, minus b squared, and I broke my tape, minus b squared. Okay, so what has to happen in order to get this is you need the a times a to get a squared, and to get a negative b, you need 1 positive and 1 negative. Okay, and once you have that, you see that the first gives me a squared, the last gives me negative b, and the outer negative ab, positive AB cancels to 0 of these ABs. So this is not something times the exact self, so that would be your final answer. There's only one way to write a difference of 2 squares. So again, we are doing this separate, so these should stand out, but when they get all mixed together, are you going to catch it? So we really want to look for these things. I see 2 terms and I see a minus sign. Definitely a difference of squares, 2 sets of parentheses, p times p. This is your first, this is your last. Your outer and your inner are 0p. So a positive 9 and negative 9. Now let's just make sure it works. P times p is p squared. 9 times negative 9 negative 81. When I go to do my outside, I got my p squared, I get my outside is negative 9p, my inside is positive 9p, and my last is negative 81. And we see that canceling and getting us right back to where we started. Now, this one looks a little different. I normally like the x to be out front. So if you're in the habit of that, you might rearrange and have negative x squared plus 25, and that's fine. But I always recommend you take the negative 1 out first. X squared minus 25. So if you do that, you would have your negative 1, and then 2 sets of parentheses. The first term is x times x. The last term is a positive 5 and a negative 5. So there's your x squared, there's your negative 25, negative 5x, positive 5x, that's that 0. And that is your final answer if you chose to take out the negative sign. Now, if you just would have jumped in and factored it as it was, that would also work. So you might also have 5 plus x and 5 minus x. Because 5 times 5 is 25, x times negative x is negative x squared. Negative 5x, positive 5x, there's your 0x. So this works, or maybe the negative 1 is distributed, so you have to watch your signs. Okay, jumping to this next one, I still have 2 terms, but I have a higher power on 4 and I have an extra variable, and that's okay, because we can do x squared times x squared. So 2 sets of parentheses here. 49 is 7 with an x squared and a 7 with an x squared. And to get the 4y squared, I need 1 positive and I need that negative to get the negative. And it's a 2y and a 2y. So 49x to the 4th, negative 4y squared, negative 14xy, x squared y, positive 14x squared y, and I got 0. There it is. Okay, so now we have a couple more complex ones to try, but I want to add on one more. So we'll call this D. Put this in here, D, and it's going to be 25x squared plus 36. All right, so take a second and you look at that. I already have a D. We'll just call this extra. Okay, there we go. Now here's the problem with this one. It looks like a perfect square, and if I go to factor this, I'm going to tell you right now it's prime. That way I don't have to scribble all over the place. This is prime. That's my answer. Okay, so why is it prime? Well, if you jump in and you try it, 25 would be 5x and 5x. 36 would be maybe a positive and a positive. And so I get my first and my last, but the outside's 30x and 30x. I don't have a 60x. And then you think, well, okay, if I change this to negative, there you go, negative 30 and positive 30 cancels, but I now made it a negative 36. So this is not going to work. Now, before we'd say it's prime, we'd have to try everything else, but there's no way I'm going to get a middle term of 0 unless I have the same factors, 1 positive, 1 negative. So it has to be a difference of squares, not subtraction. And that's the problem, guys. Okay, let's keep going here. We've got some more problems to try. So go ahead and pause this. These are a little bit more challenging, and that's okay, but we want to give them a try. All right, first thing, is there a GCF? Because, you know, I was looking, 4 is a perfect square, and watch this. 256, it's also a perfect square. So I could get this wrong if I wasn't paying attention. So the first thing I'm going to do is I'm going to take out the negative 4. And I'm left with x squared, y squared. I better take 256 divided by 4. Yep, 64. Okay. So these are perfect squares to start. Oh, I need, that should be a minus sign. Perfect squares to start, but they had a GCF. So I took out the GCF, and now I took out the negative sign, so it looks a little bit more like a difference of squares. So I'm going to keep that negative 4 here. But instead of just having an x, I'm going to have xy, xy, right? xx, yy, there we go. 1 positive 8, 1 negative 8. So let's double check that. There's my negative 64. And negative 8xy and a positive 8xy are going to cancel out. So that, again, is my final answer. Now, let's say you just jumped in and you went to the original. Maybe you took out the negative 1 because that would make it a little easier. 4x squared y squared minus 256. Okay, so if you do this and you say, well, they were both perfect squares, you'd have a 2xy and a 2xy. And the square root of 256 we said was 16. So here is the problem. It looks good, it looks like a difference of squares, but you see how you have a common factor? You'd have to factor out the 2 from here and the 2 from here, and then that 2 and 2 makes that negative 4 xy plus. That was a lot more work than taking out the GCF at the beginning. Okay, so if you left this answer, it would be wrong because it is not factored completely. So I know this takes me a little extra time, but I think sometimes it's important to know why you have to do it this way or finish it that way. Okay, now 3 is not a perfect square and neither is 108. And both of these are divisible by 3, so that's good news. Take out the 3, you're left with x to the 4th, y to the 4th, minus, I better take this and double check myself, 36. Fabulous. Okay, why is that so great? I only have 2 terms and they're both perfect squares. It has to be an even power to break it up evenly. So 3, and it'd be not xy, but x squared y squared, and then negative 36, 1 positive times 1 negative. And there's my outer and inner that cancel to 0. So if I can pick out my perfect squares and difference of squares, my factoring is a little bit easier. Hold the boats. This is not what we've been talking about. 2 terms with a minus sign is a difference of squares, right? If they're both perfect squares. 3 terms, if I had just this, it'd be a perfect square, maybe, but that is no good. Okay, so we need to think about this and figure this out. So take a pause and see what you could do, because normally when we have 4 terms, we group it and we could take an x out, but there's not much we can do there. But I see a difference of squares, but then we're stuck. So take a pause and see what you would do to attempt this. All right, so this is a tricky one. It's a little bit harder than we've seen. So if you try to go by grouping, you could find this to be x and x plus 12, and this would be 6 minus y and 6 plus y, but then you're stuck with that plus sign in the middle. So here's what I want to do. I sort of hinted at it when I said this first part's a perfect square. So let's factor this, and it would be, and we'll keep that minus y squared, x times x, whoops, and it'd be a plus 6 and a plus 6. Okay, does it work? Did we get that 12? So 6x and 6x, boom, 12x. So I really have x plus 6 quantity squared minus y squared. Okay, now think a little more abstractly. I have a quantity squared minus a quantity squared. This is now a difference of squares. So here is a perfect square. This is now overall difference of squares. So just picture this. It'd be big set of parentheses. You'd have 1 plus y, 1 minus y, but in here we'd have the x plus 6 and the x plus 6, because this would be that term, x plus 6 times x plus 6, and that is what it would look like. A little more abstract. Okay, so I've got one more for you to try. So here's an extra one, and it is 4x squared minus 18x plus 81. So go ahead and take a minute, jot that down, and give it a try. Okay, so we're back. We're going to try this. Now, here's the deal. It looks like a trinomial. I have 1, 2, 3 terms here, okay? But it looks specifically like a perfect square. So here's why I think you should write it out. It'd be 2x minus 9 and 2x minus 9. Now those aren't my only options, because I could have it as 2 and 2 or 4 and 1. 81 would be 9 and 9 or 81 and 1. I don't believe there's any other, well, 3 and 27. I'm trying to think of any other factors of 81. 18 doesn't work. 27 and 3. I think that's it. So I'm trying these. And if you jump right down and write 2x minus 9 squared and you're sure of it, you just got it wrong. And here's why. That would be the 4x squared and that'd be the 81, but the product needs to be doubled. And so if I do this, I get a negative 18x and a negative 18x. I need a negative 36x here. So it's not a perfect square. That doesn't mean it's not factorable. So for you to prove it's not factorable, you would either do factoring by grouping now, or you would do trial and error with your 2 and 2 and your 81 and 1, your 3 and 27. Flip them, you don't have to flip them with the 2's, and then try the 4 and 1 and go through everything. I'm going to tell you that this one is prime. It's not factorable, but you would have to prove that. I just wanted to show you that sometimes it looks like a perfect square, and it's not. Sometimes that you jump to conclusions, you see two terms, you think difference of squares, but that's not subtraction. Okay, so keep working on your factoring. If you can get your perfect squares and different squares down that you can pick them out, then it's going to make your factoring a lot easier, but you're still using all your same skills. GCF, trial and error, double check in the outer and inner, factoring by grouping, any of those methods will work.